Hi everyone. So in this next video, we're going to be talking about a cool application of the ratio test, and that's how we can find something called radius of convergence. So what you'll see right here is I've changed up the notation on our series a little bit. We now say that our series itself is actually going to be a function of x. So we'll see the variable x inside our series as well as that counter lowercase n. So it turns out that this is very applicable in our next unit when we talk about Taylor-Maclaurin series and power series, because as it turns out, we can actually represent almost any function with an infinite series that is guaranteed to converge at least at one point. And sometimes we get lucky and they converge over an interval, or sometimes they converge everywhere, and that's like awesome. When we can find that as mathematicians, we really like that. So that's what we're going to be talking about. We're going to be talking about this method of how we determine under what values of x a particular series will actually converge if that series is a function of x. All right, so in this case, notice we still have our sequence a sub n, but now in this case, that a sub n, it's going to have the variable n as well as the variable x inside of it. So let's look at how we can use the ratio test to figure out an interval of convergence. So remember, the ratio test is given by this. Now, the only thing I've changed right here is I've made our sequence a function of x. And remember that when we evaluate this limit, we're going to get some number called rho. And remember that if we want the series to converge by the ratio test, we need that value of rho to be less than 1. So if our limit is going to be a function of x, and that has to be less than 1, well, what we've created is an inequality. And if we solve that inequality, that effectively tells us the values x can have within this sequence that allow our series to converge. Okay? So we also have a little bit of a kind of extra mile we have to go with this, whereas in this case, when we find the places where that ratio is less than 1, we know it converges there, but when the ratio is equal to 1, the test is inconclusive, and what these represent are going to be the boundaries of our bounds. So let's say we go through and we solve for this inequality, and we get to something like 1 less than x less than 3 or something like that. In that case, we actually have to go through and plug in x equals 1 and x equals 3 into the series, see what type of series we get out of that, and then figure out if they converge or diverge at those particular x values. And that's what we call looking at the endpoints. Okay, so we're going to do all of that in an example right now. So let's say that we are given this particular series, and we want to find on what intervals of x does the following series converge. So the first thing we want to do is apply the ratio test. So again, the ratio test is no different. We just have an x in there now, but remember, you're going to be looking at this sequence when n is equal to n plus 1, and when n is also just equal to n, and doing that ratio and taking the limit as n goes to infinity. So why don't you just try doing that right now and see what you come up with on your own. Pause the video. All right, so if you gave this a shot, if we look here at this solution, oh gosh, that looks ugly, but you know, the ratio test often does. So again, in this case, notice we're just taking this sequence and we're plugging in n equals 1, or I'm sorry, n equals n plus 1 everywhere on the top, and then just the normal sequence on the bottom. Well, we'll notice a couple things immediately. First of all, we have a negative 1 to the n plus 2 and a negative 1 to the n plus 1. Well, that just results in negative 1 to the 1, so that's where that comes from. Then if we do a little bit more manipulation, we get these ratios over here, where if we have x to the 2n plus 2 and x to the 2n, well, that just goes to, it's going to end up just going to n, or x squared. Okay, that's where that x squared comes out right here. Then these 2's can cancel, and we end up with an n over n plus 1, which is just this. Now notice that if we have the absolute value sign around this entire ratio, that makes that negative 1 go away because it's going to make everything positive. And n is always going to be positive, n plus 1 will always be positive, x squared will always be positive. So when we do that, we end up getting just this term right here, and we don't need the absolute value signs anymore because everything in there is going to be guaranteed to be positive. Okay, so again, remember, we want this ratio to be less than 1 for the series converges. Okay, well, as n goes to infinity, n over n plus 1, that just goes to 1. So the limit as n goes to infinity of x squared will just be equal to x squared because there's no n inside x squared, so it doesn't matter what n goes to, that doesn't affect the variable x. So what we end up getting is this, that limit, which ended up being equal to x squared, must be less than 1 for the series to converge. So if we apply this to an inequality, this means x can be anywhere between -1 and 1, and we know it's guaranteed to converge in those bounds. Okay, but remember, that's not where finding an interval of convergence, we're not done there. We got to check these endpoints of x equals -1 and x equals 1 and see whether the series converges. So what I want you to do now is plug in these values of x equals -1 and x equals 1 into this particular series, see what series we get out, and see if you can figure out if at those points that series will converge or diverge. All right, so if you gave that one a shot, we'll test the bounds of x equals -1 first. So when we look at x equals -1, again, I just plugged in -1 for x in the original series. And well, -1 to the 2n, since n is going up 1, 2, 3, 4, 5, 2 times any of those numbers is going to be an even number. So -1 raised to an even number is always just going to give us 1. So this thing basically goes away, which obviously you don't see it on the next slide. So we end up with this. Now, if we look at this, we immediately see a -1 raised to some power of n, so we should immediately use the alternating series test. If we use the alternating series test, remember that -1 to the n goes out, and we just look at what's left, and that series must meet the 3 criteria. It turns out that series for any value of n is always positive, so that meets condition number 1. It's always going to be decreasing with increasing values of n, so it meets condition number 2, and it also doesn't fail the test for divergence, meaning that if we look at the limit as n goes to infinity of a of n, we get that that is not equal to 0. So because it met all 3 of those criteria, we know that by the alternating series test, this therefore converges at that value x equals -1. So if you weren't able to get this one, or if you kind of have doubts about what you did for the next one, try to now plug in the value x equals 1 into this series and see if you can find if it converges or diverges at that point. Okay? So if you try that, we end up getting the exact same thing. When we plug in x equals 1 into the series, we end up with the exact same series we had before, which is awesome because we already did the alternating series test on that and we know that converges. So therefore, the interval of convergence for this particular series contains both of our boundary points of -1 and 1. And so when you're solving these types of problems for interval of convergence or radius of convergence, you always got to make sure you check those endpoints. You don't just apply the ratio test. You got to check those endpoints every single time. So I will leave you now with this great example from our book. If you go to page 504, example 6, we actually did number A of that just now. But there's A, B, C, and D, and they go through pretty much every single case you could get to in doing this test for the interval of convergence. There's the one case that we just found where you have it converges at both endpoints and within an interval. It could also converge nowhere. It could converge. It could converge nowhere. Could converge everywhere. It could converge just at one particular point, which for all power series that's actually always true. Or it could converge within another interval entirely, but maybe it doesn't include one of the endpoints or doesn't include both of the endpoints. So really look over this example 6 in page 504 because it details it really, really well, and it'll be great practice for you. Now, the one thing to keep in mind is in part D, they said they needed to use this thing called the limit comparison test. It turns out you actually don't need to use that test. So when you're doing this on your own, really think about that limit when that bound when x is equal to 4, and see if there's another easier test that you guys know you can apply to determine whether it converges or diverges at that point. And so if you're done with that, if you want some extra exercises, this is a great chapter in the book for exercises for how to do the ratio test or how to find an interval of convergence. So I would strongly suggest looking at the odd numbered exercises in those chapters if you want to get a little bit more practice. So that's all I have for you right now, so come to class ready with questions.